Hi all, welcome to our channel. Today's video is on valence bond theory from coordination chemistry. This theory was mainly developed by Linus Pauling. This was the simplest theory that could explain the structure and magnetic properties of coordinate compounds about various coordinate compounds. So every metal ion when it forms a complex compound undergoes formation of coordinate covalent bond. During this bond formation, the metal ion acts as electron pair acceptor and the ligands acts as electron pair donor. To accept and accommodate the electrons donated by the ligand, the metal ion has to provide vacant orbitals of equal energies. So in order to provide vacant orbitals of equal energies, metal will provide the vacant orbitals only after the process of hybridization. Thus, vacant hybrid orbitals are provided by the metal atom to accommodate the electrons donated by the ligands. And the number of vacant orbitals provided must be equal to the coordination number of metal ion. This we can see from the example. If we take hexaamine copper, here copper will provide 6 vacant orbitals. Okay, if we take tetraamine copper, copper plus 2 ion provides 4 vacant orbitals. This is how the number of vacant orbitals provided is equal to the coordination number of metal ion. Okay, so going to the next slide, here the metal atom provides vacant orbitals of sp-d orbitals. Okay, the vacant orbitals of metal ion now get overlapped with the orbitals of ligand or ligands to form strong chemical bonds. So the benefits for the involvement of hybrid orbital is that we get after overlapping strong and stable complexes, and moreover these orbitals, hybridized orbitals, that means equivalent set of hybridized orbitals, will have definite directional properties. So these hybrid orbitals now overlap with the ligand orbitals to form strong chemical bonds. Okay, the d orbitals that are involved in the hybridization may be of two types. They are inner n-1 into d orbitals or outer n d orbitals. The complexes formed in these two ways are referred to as low spin and high spin complexes. Okay, so if inner n-1 d orbitals are involved in hybridization, then those complexes are known as inner orbital or low spin complexes. If outer n d orbitals are involved in hybridization, then the complexes are known as outer orbital complexes or high spin complexes. A bond is formed now by the overlapping of vacant hybridized metal orbital and a filled orbital of the ligand. This bond is known as coordinate covalent bond. Okay. Also, if the complex contains unpaired electrons, it is paramagnetic in nature, and if does not contain any unpaired electrons, it is diamagnetic in nature. Okay. And next, the non-bonding metal electrons occupy the inner d orbitals and they do not participate in hybridization. Okay, and one more important thing is that under the influence of strong ligands, the electrons are forced to pair up against the Hund's rule of maximum multiplicity. Okay, so when a complex it contains strong ligands, then the electrons are forced to pair up against the Hund's rule of maximum multiplicity. This can be easily understood from the examples. Okay, so here a tabular form was given to know about the hybridization and the geometry of the molecule. If coordination number is 2, the hybridization is sp with linear geometry. If the coordination number is 3, hybridization is sp2 with trigonal planar geometry. If the coordination number is 4, we have two types of possibilities for two types of hybridization. That is, one is sp3 with tetrahedral geometry and the other one is dsp2 or sp2d. with square planar geometry. What is dsp2 and sp2d here? dsp2 shows it is inner orbital or low spin complexes, whereas sp2d shows high spin complexes or outer orbital complexes. And if the coordination number is 5, we have dsp3 or sp3d hybridization with trigonal bipyramidal geometry. If coordination number is 6, we have d2sp3 or sp3d2 hybridization with octahedral geometry. So in this coordination chemistry, we mostly study about complexes with coordination number 4 and 6. So next slide is about applications of valence bond theory. So before going to applications part, we have to know about the spectrochemical series, that is the order which gives a strength of the ligands. So here we see in the middle there is water molecule, and those ligands that are present to the right side, they are said to be strong ligands, and those that are present to the left of water molecule, they are said to be weak ligands. Okay, so from pyridine to carbonyl group, they are strongly basic ligands which bring about pairing of unpaired electrons against Hund's rule in d orbitals. If we remember well about the spectrochemical series, we can easily differentiate and write the structures for octahedral inner orbital complexes and outer orbital complexes. Okay, so first we see octahedral complexes. For every complex, we have inner orbital examples and outer orbital examples. So octahedral complexes, earlier we said that the hybridization will be d2sp3 or sp3d2. d2sp3 shows that about inner orbital complexes, and sp3d2 means outer orbital complexes. Okay, and so here we took the example of hexaamine chromium example. Okay, hexaamine chromium. Here note that chromium is in +3 oxidation state and the atomic number of chromium is 24. So first we have to write the electronic configuration of chromium. So in the ground state it is organ 3d5 4s1. Actually the configuration is an exception one, because the actual configuration of chromium is organ 3d4 4s2, but due to the extra stability for half-filled orbitals, we write the configuration of chromium as organ 3d5 4s1. And in the excited state, the electronic configuration of chromium is it loses 3 electrons. So the configuration is written as organ 3d3. Okay. Now since the 3 p orbitals are completely filled, they do not take part in chemical bonding, and hence they are called as non-bonding orbitals, and they are actually omitted while writing the structure of the complex ion. Only in the present case we consider 3d 4s and 4p orbitals, and because they take part in chemical bonding. Okay, understood. 3p orbitals, as they are already completely filled, they do not take part in chemical bonding. Hence, they are called as non-bonding orbitals. In this present case, we consider only 3d, 4s and 4p orbitals as they are involved in bond formation. Okay. So, first we write the ground state electronic configuration like this. So we have 3d with all 5 unpaired electrons, 4s with single unpaired electron, 4p is totally empty. So coming to Cr3 plus configuration, we have one chromium has lost 3 electrons. So 2 d orbitals, 1 s orbital and 3 p orbitals are seen empty. Okay. So now since 2 3d, 1 4s and 3 4p orbitals, they all of nearly equal energy, and they are to be used for metal ligand bonding. Okay, that is for accommodating the 6 ligand molecules. Okay, they undergo hybridization and they give rise to d2sp3 hybrid orbitals of equal energies. So now we have 6 empty d2sp3 hybrid orbitals, and these 6 empty D2 sp3 hybrid orbitals are occupied by the electron pairs donated by 6 ligand molecules, each donating one lone pair. Okay, understood? So all these 6 empty D2 sp3 hybrid orbitals, they are occupied by the electron pairs donated by 6 ligand molecules, and each one donating one lone pair, so that we get 6 D2 sp3 hybrid bonds formed between chromium and 6 NH3 molecules. Okay, so this is about hexaamine chromium complex. This is an example for inner orbital complexes, as in this complex the d orbitals used are of lower quantum number, that is n-1 d orbitals are involved in the bond formation. So hexaamine chromium complex is a good example for inner orbital complex. And also we know that D2 sp3 hybridization leads to octahedral geometry. This hexaamine chromium complex will be octahedral in shape. Okay, also as this complex has 3 unpaired electrons, it must be paramagnetic complex. So with this it is confirmed that VB theory could satisfactorily explains the magnetic and structure of the geometry of the complexes. Okay, and D2sp3 hybridization leads to octahedral. So this is paramagnetic in nature. And if we see one more example for one more example is for outer orbital complexes. Okay, outer orbital complexes having 6 ligands. So here we took cobalt as central metal atom and we have 6 fluorine ligands. So here complexes form complex is formed by outer ND orbitals. So that is why this complex is called as outer orbital complex or high spin complex. Okay, so here we see that cobalt's atomic number is 27 and the oxidation state of cobalt is +3. So we write the ground state configuration like this. Wait. So we can clearly see now the ground state configuration 4s2 and 3d7. Okay, as the oxidation state of cobalt is seen 3 plus, it has to lose 3 electrons, 2 from 4s and 1 from 3d orbital. Okay, so again now 4s become empty, 4p become totally empty, and it is as it is an outer orbital complex, 4d orbitals will be involved in the bond formation. And so it shows sp3d2 hybridization, sp3d2 hybridization. As fluorine is a weak ligand, here pairing will not take place against Hund's rule of maximum multiplicity as explained earlier. Okay, fluorine is a weak ligand. Remember, fluorine is a weak ligand. So here pairing of electrons do not takes place against a Hund's rule of maximum multiplicity. So here the outer d orbitals, that means 4d orbitals, are involved in bond formation. That is why we get sp3d2 hybridization for cobalt, hexafluoro cobalt complex. Okay, and so here 1 4s, 3 4p and 2 4d orbitals will be involved in hybridization, giving rise to 6 sp3d2 hybrid orbitals, and these empty sp3d2 6 hybrid orbitals will be occupied by the 6 pair of electrons from 6 fluorine ions, giving rise to sp3d2 hybridization. Okay, as it consists of unpaired electrons, the complex is said to be paramagnetic complex. Okay, so this is about hexafluoro cobalt complex. Here 6 sp3d2 hybrid bonds are formed between cobalt and 6 fluoride ions. Okay, so this is about outer orbital complex, and Thank you for watching, and in my next video I'll come before you with few more examples, and we'll solve some offset bits also. Keep watching. Thank you.